Every winter solstice, I always get excited about the length of the amount of daylight we're getting increasing. And we see that here in a couple screen captures from my phone. So we've got December 21st, and then a couple days later, and we see that the day length was 9 hours, 10 minutes, 10 seconds, and then it increases by 4 seconds. And that's always kind of satisfying. It's not very meaningful. It's just 4 seconds, but it always feels good. But the part that always mystifies me is that the sunset and sunrise times are so very different. So here's the sunset time on the solstice. It's just before 5 o'clock p.m. And then here's the sunset 2 days later. It's like a whole minute later. Even worse is the sunrise. So here's sunrise 7:49, and the sun rises almost a whole minute later. So we're getting more daylight, but the sun is rising later instead of earlier. And this just seems super weird to me. And sure enough, it just keeps on going through the days. Here's December 29th and January 2nd, January 4th. Day length, it keeps getting longer by a couple of minutes, each of these little views. And sunset time keeps getting later. So that's not too surprising because we're getting more daylight. But the sunrise time, it keeps getting later, although the amount of getting later is kind of slowing down. And then finally, in sort of early January, okay, here's our day length. Here's our sunset times. They're getting later, but the sunrise finally stops getting later and starts getting earlier. Well, about time. So what's going on with this? So the answer is a little bit complicated, and I'm going to give you a really fast little overview, and then we're going to take our time and kind of walk our way through it to figure this out. So the way this works very briefly, the Earth is rotating, and this is what creates the day and night cycle. The Earth also moves in its orbit during that time that it's rotating. And so it's going to need a little extra time to rotate every day for the next sunrise to occur. Also, the Earth's orbit is elliptical, and so the Earth's speed going around the sun isn't constant. It's going to move faster and farther in January every day. And so it's going to need even more time to rotate into position for that next sunrise, which is why the sunrise is getting later for a little while in early January. So let's walk through this a little more carefully and a little slower. Now, I do have a couple little caveats. First of all, I am not an expert in this. I'm a biologist. My specialty is anatomy and biomechanics, but I really like thinking about space and trying to figure these kind of things out. So here it is. The second comment here is that none of this is new information. If you showed this video to some ancient Greeks, they would say, first of all, oh my gosh, what is this thing you call a video? Is it magic? And then after they had gotten over the fact that you're showing them a video, they would see what you're presenting and say, well, that's about right. That sounds about right. Maybe they wouldn't have known all the little factors, but nothing would be surprising here to these ancient Greeks, except for the video. Okay, so let's walk through this. Here's the sun. Here's the Earth rotating, and it also moves around the sun. Now, just a little quick point. This image of the Earth, it's a GIF file, and it's shown with a little bit of shadow at the bottom edge, just so that it looks spherical. So that's not quite accurate. The way it really works, here's the axis of rotation. So it's rotating around that tilted axis. So the half of the Earth that is facing away from the sun is in darkness, and the half that's facing toward the sun is in daylight. This red line represents the division between northern and southern hemisphere. So the northern hemisphere is getting not very much daylight here, while the southern hemisphere is getting quite a bit more. And so it's summer in the southern hemisphere, or at least it's warmer and more sunny. We get longer day length. And in the northern hemisphere, it's winter, and we don't get nearly as much daylight, and so it's colder. And then 6 months later, the Earth is on the other side of the sun. This tilt is in the same direction, though. The tilt doesn't change. That rotation of the Earth doesn't change. Here's our night side and here's our light side. And now we're going to divide that Earth again into northern and southern hemispheres. And now the northern hemisphere is getting a lot of daylight. And so it's warm there, it's sunny, the length of the day, the length of daylight is very long. And in the southern hemisphere, it's winter. because they don't get as much daylight. Here's daylight in where I live in Northeast Ohio, and sure enough, during the beginning of the year, that's right over here, January 1st, we don't have all that much daylight, and we get up to 15 hours then during the beginning of the summer, and then it goes back down. Here's the Earth and the Sun viewed from Earth's northern hemisphere. Note that the tilt of the Earth isn't shown here just because my animation skills aren't that good. And we're adding some stars in here for some context. This will be important in a moment. So here's a little person, this little pink blob. This would be a person in Southern California or maybe northern Mexico, and they are about to experience the rising of the sun. They're about to experience the sunrise. And the sun rises, and here it's noon, and then the sun is going down now. The sun just set, and now it's nighttime for this little person. And they're experiencing night. It's nighttime now. The sun has just risen. This is one complete rotation of the Earth. We're measuring this relative to those fixed stars, and that takes 23 hours and 56 minutes. Well, wait a minute, you might say. I have a watch. There are clocks. They all say 24 hours. A day is 24 hours, right? So let's explain. It takes the Earth 23 hours and 56 minutes to make one complete rotation when we're measuring it relative to those fixed stars. But the Earth also moves in its orbit during that time that it's rotating. In this picture, we see the Earth has moved a little bit in its orbit, and now that person who was about to experience a sunrise the previous day, it's still in darkness. That sunrise hasn't happened yet and needs an extra 4 minutes or so. When we measure the Earth's rotation relative to those fixed stars, it takes 23 hours and 56 minutes to rotate. We call that a sidereal day. But when we take into account the Earth's rotation and also movement around the sun in its orbit, it takes a little bit of extra time to make that rotation to face the sun, and we call that a solar day. These solar days are an average of 24 hours. Now, wait a minute. I just said an average. Why not just a plain 24 hours? Why is it an average of 24 hours instead of just 24 hours? And this is where the Earth's orbit comes in. So here is a perfectly circular orbit. We're going to pretend for a moment that the Earth's orbit is perfectly circular. Here's the Earth. Every day that passes, the Earth moves the exact same amount in its orbit. And in this case, every day really would be exactly 24 hours long. So the Earth would take 23 minutes and 56 seconds to make a full rotation relative to the fixed stars. But then to get a sunrise, the Earth would need to rotate a little bit further every day, the same amount by 4 extra minutes to get that 24-hour day period. However, the Earth's orbit is not perfectly circular, it's elliptical. And this picture massively exaggerates the extent to which the Earth's orbit is elliptical. It's not nearly this squished, but we're showing it just to make it really visible and apparent. So in this case, the Earth is closest to the sun in early January and farthest from the sun in early July. So in early January, the Earth is really scooting along. It's covering a large distance compared to its speed in July. It's orbiting faster, which means that it's going to cover a larger distance in the same amount of time. In July, it's going to cover a shorter distance. It's orbiting slower. It covers a smaller distance in the same amount of time. So in January, the Earth is going to have to rotate for a longer time to reach the next sunrise time in early January. And this is why that sunrise time is later after the winter solstice and for maybe a couple weeks until whatever it was, January 5th or 6th. Let's demonstrate this now. Here's the Earth. Here's the little person who's about to experience sunrise. And now they're in, it's high noon, and now sunset is happening, and now it's the middle of the night, and now here they are experiencing the next sunrise. So the Earth has gone all this distance, and so it has to, of course, here we're exaggerating once again. The Earth isn't going to go that far in its orbit in one day, but we're exaggerating to make it really apparent. And the Earth had to rotate for a little bit longer time for that person to experience their sunrise. in January. Whereas in the summer, the Earth is moving slower in its orbit. And so this problem isn't really going to be quite as noticeable. So in summary, the Earth rotates once every 23 hours and 56 minutes. That's relative to the fixed stars. The Earth also moves in its orbit during that time, during those 23 hours and 56 minutes. And so that by the time we're to the point of the next sunrise, the Earth needs that extra 4 minutes to catch up. However, 4 minutes isn't enough in early January when the Earth is really scooting along in its orbit. And so it needs even more time to rotate. And this is why that sunrise time ends up a little bit later. And so sunrise is a little bit later for a little while, for whatever that is, 2 weeks, I think. If you like this video, subscribe for more science and Legos and whatever else I end up posting.